Hey guys, I think it's time to get started. It is 7 o'clock. Just give another 30 seconds for people to hop in. So we've got a few more showing up. All right. All right, so I'm going to get started. Good evening. Welcome. Glad you guys could join. Really appreciate you making some time to participate in Hack the North and listen to this talk. So I am Brian Romansky. I work with Profound Impact, and we are a sponsor at Hack the North. I'm going to be talking a little bit about artificial intelligence and data integration and data normalization. This is a little bit of a travel log. It's somewhat of a background of my journey, learning a little more about data integration and data normalization, what's possible and more unfortunately what's not possible. There's a lot of things that I wish we could do, I wish I could do, that are really harder than you would think, harder than I had initially thought. My background, I'm an engineer by training, but I'm not a data scientist. So I kind of jumped into AI and data integration as somewhat of a newbie. But with a background in programming and database, high-level database utilization. So with that, let me just, I'm going to share some content and take you through some of the things that I found that I learned along the way. So share this. Cool. It's working. All right, so we're going to be talking about artificial intelligence for data aggregation and normalization. And in particular, the problem set that I've been looking at happens to be related to academic institutions, so universities, research organizations, and I'll give you a quick example of what I mean by that. So why is this so hard? What we're looking at here is a graph on the screen. This is what we refer to as an academic ancestry chart. And the data that it's showing is a series of professors at a university and the students that they mentored through their PhD program. Some of those students went on to mentor other students. And so there's a chain or an ancestry, a set of relationships from one person to many others. And of course, those people go off over time and do great things in the world. And so it's kind of interesting to look at, who's worked with whom, and can you make any associations between, the professor that they worked with and outcomes that that person produced later on. So there's a lot of interest in collecting data like this and looking at it. The interesting thing is that putting this kind of thing together is actually much harder than you would think. Now, generating the graph, the visualization of it, that's not too bad. There's standard tools to do that. But the data behind this is actually pretty hard to put together. And why is that? Well, it's because you've got lots of sources of partial data, right? If you specifically want to look at this one problem of professors and academic ancestry, you would think that the professors themselves would have the data. They would know who they had as students. The reality is, well, some do and some don't. And those who do don't have it in any kind of a standardized way or a standardized form. They might have a spreadsheet. They may have a website where they list previous students. They may have a directory full of, thesis documents and other material that, might have names of people in it. But rarely is there any one standardized way that they collect all this information. And at the university, the registrar's office, they probably have this data, but it's really not in a standardized format. Again, it's probably in a database somewhere, or maybe a sub-tab of something. It's not something they pay attention to as a topic of high level of interest. It's buried underneath some other tag or information that they track. If you could collect the publications or the thesis that came out of this graduate student work, you could probably look through that, do a text search and figure out, okay, who was the thesis advisor for all these people. But again, that assumes that you know where to find them. That assumes that you can gather all that stuff together. And then when you start searching through these, you're going to have to do a pretty complex search to figure out, well, where is the actual phrase that says, here's who my thesis advisor was. And that's not going to be a standard format as well. And of course, the students probably know, like they'll remember who their advisor was, but to do that, you have to find them first. And if you can find the students, well, then you already know the list of people. So it kind of doesn't really solve the problem because you're trying to find the students to begin with. So fundamentally, the problem we're trying to deal with here is we've got partial data, little bits of information about this problem coming from many different sources. The sources are all different types of data, and not any one of them is complete. Trying to find those sources is pretty hard, and you're trying to pull this all together into one coherent model. And this gets even harder if you want to look at few further questions. So just beyond that academic ancestry chart, there's other questions you could ask, like, hey, where are the students now, and how has their research work impacted their future research that they did or future career paths that they had? And that's actually even harder, because now not only do you want to create this academic ancestry chart, but you might want to know for all those students, what career path do they go on, what future research do they do, and how are you going to figure that out? Well, there's no one place to look for that. That's data that's out in the world. You could, again, try to search for research papers or search on people's names. You could do Google searches. Any one of these will get you some information, but none of it's complete. None of it's easy to make sense out of. So how do you do that sort of thing? Typically, if a university wants to tell a story like this, what they're going to do is hire a group of people, and those humans are going to go off and do this work. They're literally going to go interview people. They're going to make lists. They're going to go do Google searches. They're going to go on Google Scholar. They're going to go to a bunch of resources, collect all this information, and then try to make sense out of it and put together a report. Very manual, very intensive. And this is not a problem unique to academic environments, right? You see this repeated over and over again, where there's interesting questions we want to ask, and you feel like, I ought to be able to figure that out with the data, but getting the data and collecting the data, normalizing the data is really hard. And naively, when I started getting into this, it seems like this should be solvable, right? Surely this is a solved problem. We're just going to use some artificial intelligence and machine learning, and that's going to solve it. I mean, after all, artificial intelligence can drive a car. You can predict the future. You can predict the weather. You can do a lot of amazing things with this technology. Surely, if we just apply this technology in the right way, we can solve this problem, right? Well, there's certain things that artificial intelligence and machine learning is good at, and then there's a lot of things that they're not good at. So the kinds of problems that I just described, like driving a car or predicting the stock market or the weather, these are like pattern matching, pattern finding problems. So over the last 10 to 20 years, there's been a lot of really good work done on things like doing pattern matching in images, or looking at streams of data and predicting future trends for that data, looking for outliers in a data set or tagging them, filling in gaps in data. So if you have missing data, you can sort of say, well, here's what we think happened in between. You can do things that are like smart interpretations, like suggest a next step or move. So follow any kind of best practices, or as you've seen with AI engines that can play games, they're really good at looking at a series of many possible moves and making a good choice of narrowing down what's the next best choice. So those are things that AI and ML do really, really well. In all of these cases, you've got really clearly identified source of data, you've got well-defined rules, and you got a lot of training data, right? You've got historical information you can look at to say, here's what past data looks like, and you can predict what the future should look like. So those are the things that AI and ML are good at. What they're not good at is this kind of problem that we're describing here, where it's like an unconstrained search. If I want to go and find all of the grad students who worked with a particular professor, there's many different sources I could look at for that. There's many places that might give me hints or partial information, but there's no one master list. It's not like I have a database of all students that ever went anywhere, and I'm just trying to figure out, okay, what's the pattern match of students to this one professor or students to a particular research problem. That AI can do, but sort of building that table to begin with, it doesn't do so well. So let's figure out what can we do, right? Let's take this problem and break it apart. So the thing we're trying to do, this large-scale problem of finding data and making sense out of it, we can break it into a bunch of steps. Some of these steps are pretty traditional. Some of them are a little ad hoc that I've put together. But basically, we're gonna search the world for information. We're gonna go out and try to find relevant sources of data, sources of information that I can use to help me with this problem. And then got to collect that data, and then there's some nuance to that. Collecting isn't just bringing it into one place. It's really normalizing the data, right? So I may have many different file formats and different types of data, and I've got to sort of bring it into a format that I can use. The extract, transform, and load, this is a very long-lasting problem, or an old problem in data science. There's a lot of good tools out there for this extract, transform, and load, and we'll touch on a couple of open source tools for that. And then lastly, I've got to take whatever data I gathered and interpret it, right? So interpreting data is not as easy as it seems, particularly in the world of computers where you're trying to automate things. The problem you run into a lot is data formats can differ, right? So a good example is date format, right? It's pretty straightforward. Humans are pretty good at recognizing lots of strings of characters and numbers and figuring out, oh yeah, that's a date, and I understand what that date is. Computers have a really hard time with that, right? If you don't give them some hint as to what this thing is and give them a sense that this is a date and not something else, it's actually much harder to make sense out of that. Although that is touching on one of the problems that AI can do, and maybe it can help us. So there's points along this path where machine intelligence and AI can help make things better, but it's not going to solve the whole problem for us. So let's go step through these individual pieces, and let's better understand what tools are out there, what they can do, what they can't do, and we'll come to some conclusions from that. So first, on the search part, you're well familiar with typical search engines on the internet. Obviously Google or DuckDuckGo are the leading search engines out there. What we're finding over time is that there's a growing number of vertical specific search engines, right? So Google is a horizontal search engine. You can put any kind of a question in there and it's going to search the world, search the web for any relevant data. It's going to look for anything. And one of the problems there is if your search is unclear or is ambiguous, if it's just a name or a topic, it's going to give you lots of various types of information that might be related to that topic. It's not going to be very specific to the thing that you want to do. So if you could look back at my initial problem of I'm trying to find students and their academic ancestry, if I put in a university name, well, I'm going to get, how to apply at this university. I'm going to get, all kinds of events and activities at the university. It's not going to give me stuff that I really care about. If I put in a person's name, I'm going to find out lots of information about the person, but not necessarily stuff that I really want to know about. A vertical search engine is basically replicating the capabilities of a traditional search engine, but designed specifically for looking at particular types of information. A good example might be healthcare, right? A vertical search engine might have really detailed information about health histories, health outcomes, drug interactions. And so there I could put in a search, about maybe a drug or a symptom or a disease and get really relevant information out of it. And it knows what I'm looking for, has a sense of what I'm trying to do. So for this type of problem that I'm working on, really what you want is a vertical search. You want something that's very targeted at the type of information you're looking for. A good example of that in this instance would be Google Scholar, right? It's a subset of the Google database that just looks at academic research papers and academic research outcomes. And so that's one example of a vertical specific search engine. It'll give me some of the information I'm looking for. There's also some tools out there now where you can build your own vertical search engine. So there's actually some platforms where you can sort of define what data sources you're looking for, what kind of data you want, and train it to do a particular type of search. And it can help narrow down what you're looking for. And now, because of these platforms, you're seeing a proliferation of hundreds of new vertical specific search engines trying to draw traffic away from the generic search engines like Google and Yahoo, and really getting people to target or go to a targeted or focused search engine. And you see that, as I mentioned, for healthcare, for legal applications, for automotive. If you're trying to buy a car or sell a car, there's specialized search engines that'll help you do that. So there's a whole world now of new search engines that are targeted at a specific thing. So in our journey to try to put together a chain of events to do a broad data search, the first step you're going to do is try to build a custom vertical search engine that's targeted at the kind of data that you want. The next problem you're going to face, though, is collecting. So now you've done a search, you found lots of potential sources of information. Some of that might be web pages, some of that might be files that you can download. Some of that might be pointers to third-party sources where you can either buy or acquire data files. The problem now is to pull all of these different types of data, different types of media into one place. And that's actually pretty hard to do. So this data aggregation problem, there's lots of tools that can do that. They have various levels of sophistication and automation. I've listed here a few. These are all from the Apache open source community. There are many other tools, but I chose these because they're open source. They're available to hackers. They're available to people who are trying to piece together a problem, and they approach the problem from slightly different ways. So Apache NiFi is designed to be a graphical tool where you can sort of point and click and design a workflow. You can design a series of steps to say, go get a file from this particular source and then do some sort of a transformation on it and deliver it somewhere else. You can even trigger events with Apache NiFi. So the first step might be go run a vertical specific search, take the results and filter them somehow, and then go get specific files from that search result and do some processing on them. It's a very powerful tool, but of course, as a user, you have to be pretty knowledgeable about what you're trying to do. It's not going to solve the sort of magic problem where you would love for an AI engine to figure all that out and create the tool chain for you. But if you know what you want to do, you can automate and make a process repeatable with that. Stream sets is basically a rules-based transformation engine. So it's a little bit like NiFi in that it's a very powerful engine. But instead of having many to many, it's really kind of a one-to-one. You define a set of rules and it figures out how to do a transformation, but it gives you a lot more options in terms of how to do that transformation. Airflow is designed to be a task scheduler. Again, these overlap. It can be combined with NiFi, it can be combined with stream sets. But Airflow is intended to trigger events and trigger activity. So if you wanted to have one type of, say, a publication of a paper, go trigger a search for other things related to that, Airflow would be a good way to do that. And then Kafka is a tool that also can create these complex workflows, but it's more programmatic, whereas NiFi is graphical and you can kind of point and click. Kafka is really more industrial grade for large scale data sets. And if you've got a lot of repeatable patterns, it's used in a lot of corporate type of environments where if I want to connect my cash flow system to my accounting system to my order to cash payment system, Kafka is a good tool for that. It's a little more complex to use, a little more complex to set up, but it can do very powerful things. So this data collection, data understanding is sort of step 2 in our process, getting all the data into one place. The next thing we're going to do is this classic problem of ETL, extract, transform, and load. This is a very old problem in data science, been around for a long time. Historically, programmers have done this ETL process very manually. So, when you had to move data from one place to another, or you had to transform data from one data type to another, basically you'd start writing code from scratch and you'd write an application to do an ETL. Over time, the tools have gotten better, but it's still a pretty manual process to train a system to say, I want you to take, let's say all of the headings from a particular file and put them into columns in a spreadsheet, or load them into a database in a certain way. And I want you to normalize all of the dates so that they all have a particular format so that automation can handle that later on. That training process of mapping many data sources to one data destination and explaining how to do the data transformation is a very tedious thing to do. Now, there are some open source tools here that can help with this as well. Hivo is one. It's a no-code data pipeline, kind of like Apache NiFi that I mentioned earlier. You can graphically lay out a sequence of steps that you want to do. It can discover information about data. So within Hivo, when you have data loaded into there, it will surface or show you what it's found in the data and make it pretty easy for you to sort of, point and click and say, okay, I want this field to go here. I want that field to be transformed in a certain way. Logstash is a platform or a tool that's evolved quite a bit. It's open source, although if you really want the high performance version, you're going to pay for it as part of the AWS Elk stack. It's built into the Elasticsearch engine. It has a nice plugin architecture. Again, can do lots of data transformations. And then Talend is another graphical workflow editor. It's similar to Hivo. Again, has an open source version, or you can pay to get a higher performance, higher scale version. So these are all tools that help solve or eliminate the amount of coding that you got to do to sort of take data out of one file type and put it somewhere else. They help make the problem better. None of them solve the problem all completely and automatically. And that brings us to this next step of sort of interpreting the data. So this is a term often referred to as data cleansing, data wrangling. Sometimes you'll see the term data monging. The idea here is that, this is that last step of really getting data into the format that you need, cleaning the data, filling in missing data steps. So a lot of times you'll collect data from multiple sources and you'll see, okay, I've got data from various years or various steps in the process, but there's a few that are missing. So I have to guess as to what they are. A good example might be weather data. Like maybe I've got, rainfall data from a bunch of historical dates, but there's some that are missing and my algorithm is expecting to see a clean set of data. So I'm going to fill in or approximate the missing data in between. So that's a place where you're going to use, some sort of a matching algorithm to guess what those data points would be in between. Again, historically, this is done very much manually. People would literally look through series of numbers and look for outliers or look for things that have to be fixed. You can see some fun quotes here. A team from Google Research, had done some studies to look at past work that was done in data cleansing. And they pointed out that everybody loves to do the model work, but they really don't like to do the data work, right? So people really like the cool, sexy part of AI of running algorithms and showing interesting results. But they kind of hide the fact that to get those cool results, you had to do lots and lots of upfront work to massage the data, to clean it, to make it match your what your algorithm can handle. And they actually point out to a term they refer to as data cascades, where actually sometimes the way you choose the data that goes in and the changes or the manipulation that you do in that data before you run your AI algorithm can have a huge impact on the results that you get. And they refer to this as a data cascade, where early assumptions about the data or filtering that you did on the data can have a big impact on the insights or the results that you can get out. And you may not even realize the connection between one and the other. Another quote there that, 95% of data scientists' time is spent doing this data wrangling, data fixing, and yet, almost all the data scientists really hate this. Like, this is just not the fun part of the job. This is the really tedious, complex part of the job. Surprisingly, there's not a lot of automation. There's not a lot of work that's been done to really fix this thus far. It's this painful step in the process that these AI researchers kind of deal with and put up with. But only a handful have really done much to try to automate or fix the problem beyond the types of tools that I described earlier. Ihab Elias at the University of Waterloo has done some work on this. He's really called out the need for help, the need for automation and tools to make this better. He and a team of fellow researchers have created a tool called HoloClean. It's a statistical inference engine. Basically, it will run an algorithm across data and look for those outliers, look for those missing data points, and automate the process of filling them in so that researchers don't have to manually do that. It has some other tools, and over time, the tool's gotten better and better and more automated at the process. And so their vision is to improve this tool and add more automation to it so that you can eventually take a lot of the manual, tedious steps out of this data cleansing. One of the things about that HoloClean engine that I thought was really interesting is that the way they think about data is a little different from some other engines. They tend to think of a data cell as a random variable. So if you imagine, let's go back to weather data, for example. So if I have rainfall data across several different days, they'll look at the rainfall data on a particular day as a random variable. And then they'll look for data that confirms or denies what they believe about that random data. So if you have multiple sources and multiple inputs that are feeding into one data set, this model will say, I've got this random variable and I have many different influences that are telling me what they think the actual rainfall was on that day. Some might be more reliable than others. Some might be more easier to interpret and understand than others. So I'm going to take this collection of all these inputs and make a decision about what I think is the most probable outcome for that particular rainfall on that particular day. Try to map that against our problem of the graduate students, you could say the same kind of a thing. You could say I have a professor and I can assume that every year they have a certain number of students that they were advisors for, or the advisor for. And then I could try to fill in that information, and I could say, well, look for evidence of who could the students be that worked with this particular professor. If I find a thesis that names the student and the professor, that's pretty good evidence, pretty strong evidence of a match. I might find, data from the registrar's office that confirms that match. I might find partial data for other people. So I can sort of build up this data set by collecting data from multiple sources and trying to interpret this and make sense out of it. But this is definitely a work in progress and not a solved problem. And I found more and more evidence as I kind of dug into this that a lot of people realize this is a problem, but it's definitely not a solved problem yet. So with all of that, what's my take after my journey through this on the state of the art of data aggregation and normalization? I wish I could come to you guys and say, here's a recipe or a method of doing this, and it works, and it's reliable, and it's repeatable, and you can deal with any kind of ambiguous data in this prescribed way. My take is you can't do that. This is really hard to do. It's a complex problem, and it touches on a lot of bleeding edge areas of data science. So I kind of took you through those multiple steps, and every one of those steps is really hard to do, and every one of those steps is sort of an active area of research. None of them are fully solved yet. It's going to continue to be hard for a long time because this really isn't the kind of problem that aligns well with the current artificial intelligence or machine learning capabilities. This problem of sort of getting unconstrained sources from unknown data types from unknown data sources isn't really what works well, right? AI/ML works when you can say, here's a data set, go find something about it or go look for patterns in it. But if I'm just going out to the world and saying, I don't know where to find this stuff, but please help me find information about this, that's where, unfortunately, humans still do a much better job than machines. And I think we're going to need to have humans in the loop for a while. However, the good news is it can be done for a targeted set of problems. So if you know that there's a particular sequence of information that you're looking for, sort of the recipe, such as it is have a set of humans do it, which is the old school way to go out and do this research, but shadow them. Like, look at where they go, look at what questions they ask, look at what data sources they go to, and then take some of the tools that I have just talked about and look for ways to piece those tools together. The tools can make the process work better. They can help the humans do a better job. They can help fill in some of the gaps. And once you work through the process once with the human, hopefully you can, at least for the few sources you've identified, the few data paths that you put together, you can at least make that portion of the process repeatable. You still might need some human inspiration and new ways to look at the problem over time, because it's not going to be static. You may have to dig up new data sources and add them into your mix. Some of your data sources are going to change, so you may have to go back and fix things that break over time. But for a very targeted set of the problem, once you've gone through and created this tool chain, you should be able to make a repeatable process. And my view on this is it's kind of exciting because it's a great opportunity space for hackers and entrepreneurs. So if there is a problem set that you see out in the world where, collecting data from a variety of sources and making some sense out of it and delivering back some insights or a visualization or a report or some sort of an update based on some complex data combination that you see in the world, that's really hard to do. But if you can create that tool chain and you can create the data normalization process out of it, you can create some real value. So it's a really good place to go as a hacker. And some of the tools that I mentioned are all open source tools that you can download and play with and learn from. And if you want to start a business, maybe it's even something you can look at as a way to create real value for end users. So that is my take through data normalization and AI technologies in the state of the art. I'm happy to hang around if anybody has questions. I assume you can throw them into the chat window. I'm not sure if you can speak in audio or not, but I'm happy to hang around for a while and answer any questions you got. So I could ask, have anybody online, anybody who's still hanging in there, Have you come across any problems where large data sets actually matter? Right. So I use the academic example as a data set. I mentioned weather. I mentioned healthcare. Anybody stumble upon a large, complex problem with undefined data that you think is worth solving? Stocks. Okay. So yeah, the suggestion there is stock data. So financial data is so stocks are interesting, right? Because um, historical stock data is all pretty clean and automated. So running an algorithm on just looking at the price of a stock is pretty straightforward, right? But that's not going to tell you a lot. In other words, just looking at the historical data, well, everybody has access to that, and all the algorithms have access to that. So all the AI algorithms are going to come to similar conclusions based on historical data. What's really interesting about stock data is if you can bring in independent sources of data, like, if you're looking at oil prices or oil companies or something like that, obviously weather can have a big impact on shipment of oil or pumping of oil, or geological events can have an impact on oil usage trends. News and information may have an impact on oil prices. So the more independent sources that you can pull together, now you've created something of value, right? So just looking and running an AI algorithm on historical stock data, not very interesting. But if you can use these techniques to pull in independent third-party sources, and you've got access to some sort of a leading indicator that others don't have, that's really valuable. Somebody else suggested news and stuff. And certainly, if you want to know the latest information about a particular topic area, right? So there's news, and news is very generic. It's almost like a general purpose search engine. Just watching the news doesn't tell you a lot. But if there's a particular topic that you care a lot about, let's go back to the stock example, right? If you want news about a particular company, well, now that's a more interesting problem. Certainly, you can do filters and trigger events based on news if a company's keyword is mentioned. But there might be secondary effects, people who work at that company, what they do, or community around where that company is located and what's happening there. Adjacent companies. There's a lot of secondary effects that might actually matter. So if you can build a tool chain that pulls in lots of disparate data related to a company, you could probably do a better job of predicting its stock price or understanding where it's going. Somebody suggested here manufacturing efficiency. That's another really hard one. So certainly, if you're in a manufacturing process where raw materials vary quite a bit, you might want to put together a tool chain that informs, the quality or supply chain of your raw materials, and that can have a big impact on your planning. So I assume that's another place where this type of technique could really matter. I think, if you take any kind of a predictive situation, you could find a reason to pull in third-party data sources. Yeah, somebody mentioned IoT, certainly. So the proliferation of devices producing data is certainly a way to feed into this. Now, IoT data tends to be pretty well normalized. Like, that's pretty well constrained data, pretty consistent data. So one good thing with the world of IoT is that a lot of the data can feed into a predictive model or a digital twin style of model where you can create an algorithm that tracks the performance of an asset or a machine or trends in a particular environment. So IoT data actually lends itself really nicely to AI and ML processing. It's one of the reasons why it's such a hot area, because you're getting really good quality data from a predictable source, and you can do a lot of algorithmic processing on it. It's very different from the sort of lumpy, unexpected data coming from unplanned sources, right? So very different from news and events or other things where you really don't know what to expect, and you're not even sure ahead of time what information is going to be relevant. Cool. All right, well, I think those are really great suggestions. I hope this was helpful to somebody and somebody's going to go out there and do a great hack. I hope you guys are having a great time with Hack the North. At Profound Impact, we do have a sponsored challenge out there around visualizations. And there we're really trying to figure out, looking for people to help us map these very graphical visualizations to ways that people who have different capabilities, different abilities can understand them. So if you have any ideas of how to fix that, please let us know. All right, thanks everybody. I'm going to hop out. Have a great hack.